Whenever we've been traveling downhill, we've always been going straight down. We've never had anything actually roll and tumble head over heels from one location to another. Rotational kinetic energy is just like regular kinetic energy, only with an extra term that accounts for the head over heels motion. If we're looking at a conservation of energy problem with something rolling down a ramp, something heretofore has had wheels, we've always checked in with the gravitational potential energy, MGH. We've always checked in with the kinetic energy, a formula we've taken for granted, with a 1/2 that comes from calculus, a letter that stands for how hard you are to move, in our case mass, and a letter that stands for how fast you're moving, in our case linear or translational velocity, v. For the first time, though, we notice that things that start at the same height don't end at the same speed. There are clearly winners on this race and losers on this race. We saw in class that the shapes with material more compactly centered around the axis of rotation, which, by the way, is not always in the center, tend to roll more quickly. A full sphere is rolling faster than a hollow sphere, and a filled cylinder faster than a hollow cylinder. From here, we took the analogy that if we have a letter for how hard you are to spin, which depends apparently on your radius and how compact you are, and another letter for how fast you're spinning, whether or not you're traveling or you're just a planet rotating around an axis in one place, we can put them together to find a formula for rotational kinetic energy. Let's see what this looks like with numbers. Please note that rotational kinetic energy and translational or regular kinetic energy are not mutually exclusive. You can have them both at the same time. There's no reason to assume you just have one. For instance, let's take, well, not going down a ramp, but going up a ramp. You roll a bowling ball up a ramp. How far up the ramp is it going to go? Please note that nobody in a real bowling alley takes a meter stick to this to find h, the height up a ramp that the bowling ball is going to go. You're more interested in L, the diagonal distance up the ramp. We'll use lowercase l because uppercase L is going to be reserved for something else. Set up your before and after. As before, we've got a mass of m, a radius of r, and an initial velocity of v. Press pause, set up your conservation of energy, and press play to check your work when you have all three variables with equations. Ready? Check. Bottom of the ramp, before you've gone anywhere. Gravitational potential energy is 0, nothing stretched. You are moving. Yes, you're moving. You are moving up the ramp, 1/2 mv squared. Are you rotating? Yes, you are also rotating 1/2 I omega squared. If you've got these three, you're good to go. Now add them all up to find your total energy. Please note that you will need to make 2 substitutions. Make them at this juncture. Do not wait. You will wish you hadn't. Look up I, the moment of inertia. We are assuming for the moment that a bowling ball is a perfect sphere of constant density. Physics of bowling will tell you that it isn't, but we'll assume it is. Look up the moment of inertia for a perfect sphere of constant density. Thick sphere, solid, not hollow. Then, omega. Omega is angular velocity, how fast you're spinning. Look up, either in your class notes or in your textbook or on Mr. Google, the conversion. Notice that how fast you're spinning is directly proportional to how fast you're traveling. Make those substitutions. Show your work very, very carefully. Watch for copying errors. Here, don't lose that 1/2, and here, don't lose the squared. Simplify. You'll find lovely, lovely like terms. When it's as simple can possibly be, and so you say, "Mwah, that's beautiful," press play to check your work. Pause. Ready? After all said and done, did you get 7/10 mv squared? Good. You got more energy here than if you were just traveling straight up the ramp. Now, after you've gone straight up the ramp, what happens to that energy? Finish up the after column, go as far as you can go, press play if you get stuck, or to check your work. You want to find out how far up the ramp it goes. Do that the best as you can. Ready, set, go. Alright, business as usual. By the time you finished up the ramp, it's not moving, it's not spinning, all the k terms are going to be 0. How much of that 7/10 mv squared goes to gravitational potential energy? All of it. There's your mgh, and now you can solve for h. Hey, that's pretty cool. Well, they didn't ask for h, they asked for L, but I think we're almost there. See the angle of the ramp? It's given in the problem. What's more, sine theta, right triangle, draw that in on your notes, make sure you've got h, L. Hey, sine theta is h over L. That means L equals h over sine theta. Finish up the problem, press play to check your work. Ready? If you got something that looks like this, you're in good shape.